Darrell Lee Berry Jr. back with some more quantum physics, part three of this foray into a quantum harmonic oscillator. So I want to make sure to try to finish this series here, and I'll review what we did so far. So we started with discussing the classical harmonic oscillator, how it relates to a quantum oscillator. We took the time-dependent Schrodinger equation and substituted g in for it to simplify it. Then earlier we did the power series, in which we basically got a polynomial type solution for the differential equation as a simplified solution compared to solving the original Schrodinger equation. I had to plug that into equation 2.79, which the book seemed to label 2.8 mistakenly. And we went ahead and eventually got the recursion formula, which allows us to get the uh, coefficients for H. So we were ended here. These are the coefficients for Z. So did I leave off I left off one of my Z's here. So this will be a G as well. All right. So the odd number, it's the odd numbers, the even will give us the even numbers. You're welcome who joined. Be sure to drop a line. Subscribe if you haven't. And I'll see if I can finish this before my gravity stream that's upcoming. While shares will be a less mathematically intensive. Uh, Even though I'll do some math, but I'll share an interesting thing I learned from my relativity professor, who was also my classical dynamics professor last semester, about gravitational potential and what it means about orbits. So be sure to come check that out. So it's saying so H even psi plus H odd psi gives us the full answer, or Z gives us the full answer. We have two arbitrary constants that allow us to start the process. Not all solutions are normalizable. Right. However, not all solutions so obtained are normalizable. For at very large J, the recursion formula becomes, so it's saying at very large J. So if J is very large, we end up with basically, so this is a J here, this is a J, this is a J. So at very, very large J, the 1 and the 2's don't matter here. It ends up being J squared in the denominator and J at the top, so that leaves just a J at the bottom. And we're assuming that J is so large that this doesn't matter. So that's why at very large J, you end up with just 2AJ over J. So I see what they're saying there with their approximate solution. Okay. AJ is similar to C over G over 2 for some constant C. It's not as intuitive. They're saying that J is really big. And it shows at large Z, where the higher powers dominate. Right? H goes up like exponential Z squared. then psi, remember psi, that's what we're trying to calculate, goes like exponential. And psi goes like exponential e squared over 2. And we're in the equation 2.78. This is 2.78 here. It's precisely the asymptotic behavior we didn't want. There's only one way to wiggle out of this. For normalizable solutions, the power series must terminate. So all of that to say that this power series solution here can't go on forever. There must be some number j that makes term equal 0. So some number j at some point must make this term equal 0. It's pretty much all they're saying right there. There must occur some highest j, called an n, such that the recursive formula spits out a n plus 2 equals 0. This will truncate either the series h even or h odd. The other one must be 0 from the start. A1 is 0 if n is even, A0 is 0 if n is odd. For physically acceptable solutions, then equation 2.82. So this is 2.82. Right, so that's 2.82. So k equals 2n plus 1. First, let me rewrite this as n, because now they're talking about n. So we'll say a n plus 2 equals a n 1 minus a plus 2n over n plus 1 n plus 2. So if I was to simplify this according to the lines they're saying, we have a n 2n plus 1 minus k over n plus 1 n plus 2. And they're saying that for some n, so basically in order for this to be 0 at some point, to be 0 at some point, somewhere, k must equal 2n plus 1, which means that an 2n plus 1 minus 2n plus 1 equals 0. So thus, at some n, all right, or some positive energy n, which is to say, referring to equation 2.74, which I believe I labeled. Sometimes it's hard keeping up with the different equations. So that was way back in the day. Did I even write that one down? I didn't. I'll write it here. So K equals, or is defined as 2E over H bar omega. I remember writing that down somewhere. I didn't. I don't like when I miss right now in the equation. All right. So 2.74 is that. So that's how we define K. So the energy must be E equals K H bar omega over 2, solving for E. And K must be 2n plus 1. So that's 2n plus 1 H bar omega over 2. You divided that in. So E equals n plus 1 half. So let me actually break this up into a few steps. So we have 1 over 2, 2n plus 1 H bar omega. And I'll distribute this into there. So we have n plus 1 half H bar omega. And thus the energy for the uh, quantum oscillator, I'll just say SHM, QSHM, equals n plus 1 half H bar omega. So that's why the energies have to be that for n equals 0, 1, 2, and so forth. And some n causes that whole thing to equal 0. Right, so that's a good way to remember what the energies for a harmonic oscillator or quantum harmonic oscillator must be. Thus, we recover by a completely different method the fundamental quantization condition we found algebraically in equation 2.62. And remember, we skipped that step because this step will help us with the hydrogen atom as well. It seems at first rather surprising that the quantization of energy should emerge from a technical detail in the power series solution to the Schrodinger equation. Let's look at it from a different perspective. Equation 2.71 has solutions, of course. Let's find 2.71 right here of any value of for any value of E. In fact, it has two linearly independent solutions for every E. But almost all of these solutions blow up exponentially at large x and hence are not normalizable. And that reminds me why that exponential from the last video, why we had to eliminate that positive exponential because it has to be normalizable, meaning integration from negative infinity to positive infinity, the area under that curve has to equal 1 for it to be normalizable. Thus, we have a 100% probability of finding a particle somewhere, but not more than 100% probability. Imagine, for example, using an E that is slightly less than one of the allowed values, say 0.49 h bar omega, and plotting the solution. That's figure 2.6a. This one is right here. Now try an E slightly larger, as this one B. The tail now blows up in the other direction. As you tweak the parameter in tiny increments, from 0.49 to 0.51, the graph flips over at precisely the value 0.5. Here, there's a solution escape exponential asymptotic growth that renders it physically unacceptable. It's pretty interesting. So only at that precise value. So basically, any more than the precise half causes asymptotic behavior to plus or minus infinity. Right. See what they do here. For the allowed values of k, the recursion formula reads. So basically what I'm going to do is plug in allowed values for k. N plus 2 and k equals 2n plus 1. Isn't that go to 0? Let's see here. Let's see what happens. N 2n plus 1 minus 2n plus 1. Yeah. So how did they plug that in? For the allowed values of k. Oh my gosh. So they left the two letters. Hold up. They kept everything else is J. So this would be incorrect. They kept everything else is J. Only put in literally for K. We have that. And what I'll do is literally input uh, K equals 2n plus 1. So that means AJ 2J plus 1 minus 2n plus 1 over J plus 1, J plus 2. So we have AJ 2J plus 1 minus 2n minus 1 over J plus 1, J plus 2. So we have what the book has now almost AJ 2J minus 2n over J plus 1, J plus 2. So AJ plus 2 equals AJ, and then we have the AJ at the end. -2 n minus j over j plus 1, j plus 2, AJ. So that's what the book has right there for equation 2.85. If n equals 0, there is only one term in the series. We must pick A1 equals 0 to kill H odd. J equals 0. Hence, right, let's actually do this. So if n equals 0, we have A j plus 2 equals negative, that's 2j over j plus 1, j plus 2, AJ. So n equals 0. So that is the only term. So j must equal 0. J equals 0. We have A2 equals 0. There is a J right here. Right? So that does yield A2 equals 0. So to go back to that original H, it seems. I remember where I put uh the solution to get H. That's the part I'm missing. So this matches the book. HOG equals HO. Let's see if I can find the equation where they're solving for H's. Oh, it must be it, right? No. It must be this. So HOZ only has the I'm going to ask about this one. Uh, oh, from the previous section. We got most of the way. Okay, okay. I think I'm starting to remember where this H equation comes from. Forgot what they're called though. Heuristic equations for it's something with an H if I remember right. Okay, they are. Hermite polynomials. See how they're getting it though? A2 equals 0. So H naught E equals A0. Oh, I see. I got you. I got you. It's because since A2 equals 0, the only term available is H naught because odd equals 0. So that means this has to only equal A naught. All right. It's because all the odd terms, if you pick an even, all the odds are 0. And since A2 is 0, only term is A naught. Thus the first term, we can say Hn, H0 is A0. All right. So that means that psi 0 of Z equals, and where did I put that? A lot of equations to keep up with. Here, 2.78. Again, that's the original thing we wanted to solve for with psi, the wave equation. So put an in here. So psi 0 equals, so H naught H naught Z E negative Z squared over 2 equals A naught E negative Z squared over 2. All right. Which apart from the normalization reproduces equation 2.60. Let's try n equals 1. N equals 1. And welcome those who are watching. Be sure to drop a line, say hi. If you have any questions, let me know. I'll be closing up in a bit to talk about gravity, but I do want to try to finish fleshing out some of these equations. So n equals 1. We have odd now. We have uh, this equation we're going to plug in. I should copy this down. We have aj plus 2 equals -2, 1 minus j over j plus 1, j plus 2, aj. N equals 1. We take a0 equals 0. All right. So n equals 1, a0 equals 0. Take n equals 1. That's this. A0. So even should be 0 now. Even equals 0. A2 equals 0. Here, A1 equals 0. So A0 equals 0. A1. So A1 plus 2 equals -2. 1 minus 1. That's still 0. Yep. Over aj, that equals 0 from this right here. So A3 equals 0. So H1z equals A1z. So they're getting it from that. All evens are odd, so A2 equals 0. A3 equals 0, so it doesn't go to A3. So it stops at A1. Right? So now we have also plug in the equation psi 1 z equals H1 z e negative z squared over 2. So that equals A1 z e negative z squared over 2. Yeah, I got that right. A1, C, E. Yep. Let's try one more. These are called the Hermite polynomials. As they get complicated. Try one more. From those who join, I shall be back momentarily to talk about gravitational potential and uh, the effects on orbits. So be sure to come back momentarily. I'll try one more of these Hermite polynomials and then I'll stop this stream and start a new one. So those who are watching, be sure to come right back in a bit. When this stream ends, we'll have a relatively lighter discussion about gravitational potential energy and orbits. So now we have n equals 2, which is even. So all the odds going to equal 0. So we end up with aj plus 2 equals -2 minus j over j2 j plus 1. That's our equation with a j at the end. And for n equals 2, j equals 0. So j equals 0 yields a2 equals -2 times 2 over 2. So that equals -2. Oh, equals +2. Why am I getting -2? For n equals 2, j equals j equals 0 yields is -2. J equals 0 equals -2 a naught, right? J equals 2. So j equals 1. Give us 0. I don't know why they skipped j equals 1. Let's keep going. Let's see. What happens if we put in j equals 1? Oh, that's odd. All the odds are 0. All right. So j equals 2. That's a4 equals -2, 2 minus 2. So this zeroes out. It doesn't matter what this is. This equals 0. So a4 equals 0. So a2 is the last term. So now we have a0 and a2. The last one. See what this gives us. I have to look at this again. They're kind of complicated. So H2 equals all the outer zero. So we have A1 Z A0 plus A2 Z squared. This is H2 Z. So that equals A naught plus an A2 is minus 2 A naught Z squared. This is starting to make sense. So this is equal to A naught 1 minus 2 Z squared. All right, here we go. So that means that psi 2 Z equals H2 E. So that's A 1 minus 2 Z squared. And then we have e to the negative Z squared over 2. Right. That's what they have. All right. And these are the Hermite polynomials. That's a good place to stop. So we finally solved the Schrodinger equation up to a certain point. Basically, they taken simpler, I guess maybe not simplified, but codified the Hermite polynomials in the solution into a simpler form. Maybe I'll come back another time and review that. I think this is sufficient for now. And I'll be back in a little bit and I'll talk about how gravitational potential energy relates to the orbits of planets. So give me a few minutes, I'll pop right back on. See y'all in a bit.